Did you get 10? Okay. Alrighty, so let's keep going. Alright, so here's our meter stick again. Here's my axis of rotation on the end, so therefore our moment of inertia is 1/3 ml squared. We're going to say it's a 1 kilogram. Go ahead, find your angular acceleration. Look how cool it is if I don't put numbers in. And then we can just use 10 for G with all of these examples. It just makes life easier. Unless you already did it. Very well. Just a second. Is that what you got? No? Where's the what? Oh yeah, double checking the math. Let's see. This L goes away. One of them and this one. And then this goes and this goes. And then the 3 pops up, the 2 drops down, and then we have a G over L, so then that's 3 times 10, and then that should be 5.1, right? Oh no, it's times 1, duh. I'm sorry, it's 1 meter. Yeah, same, that's okay. You have me thinking though, Emma. I just like, because I have 1 in my notes, and I'm like, wait a second, is it half of 1? Is it what? Okay. That's okay. You can feel my own brain sweat as I'm trying to put these together. All right. All right. How are my virtual people doing? Did more people come? Or is it still this? Let's check and capture some names. Yay! Someone else came in. I don't know. Guanye. Yay! Save username. All right. Any questions with you guys are gonna have to unmute, okay? If you have questions. Here's my question to you. Are you gonna have when it gets here, is your angular acceleration going to be higher or lower than it was before? What do you think? Your angular acceleration. Tell me how you tour. It would, why? Yeah, because only part of this force now is going to produce a torque. So, like what Emma was saying, because only the part that's perpendicular, so your torque is going to decrease. So you will have a lower angular acceleration. Because only this part of the force produces the torque. Awesome. Okay, so it would be from your axis of rotation, here's your R, and then here's your perpendicular part. So you'd be using this theta, so it would look like F R, but you're using F cosine theta. Because here's your F. You'd be using F cosine theta times all of R. Because, go ahead. So in this case, we're taking the perpendicular part of R. No, hold on a second. The perpendicular part of F with R. So we're still using, did you watch, okay, so hold on a second. Real quick, did you guys get to watch the examples that I posted after? Okay, that'll help because that cleared up this one. And then it went through another couple of examples for your torque. So those are high on the priority list, the ones that I sent, that I texted you guys about and said I uploaded them. But then I said, then there's two versions of it. One I tried to do through PowerPoint and then the sound didn't work. It had like little sound, but none of it was just the solution. Then I actually went and revisited the video and made the video. So if you go ahead and do that, I'll summarize it real quick though. So what happens is, we know that to do torque, to get torque, we're going to go R cross F. And that means that it's either going to be the part R perpendicular and all of the force, or all of the R, the distance from the axis to the force, and the perpendicular part of the force. That perpendicular part is that sine theta. That's incorporated with that. So you can, my force is right here, straight down. So if I took R, and then I just want this perpendicular part, that is taking into account this sine between those two. Like we just want that perpendicular part. So it doesn't matter, again, it doesn't matter if we broke up it's one or the other. And then by doing that, by taking the perpendicular part, that is doing the sine between the two. So it's sort of like work when you did work, just the opposite because now we use the sine. Okay, so speaking of that, I'm doing work with the CP kit. So if I mess up my angles, that's why. Or if I talk about work, that's why too. Okay, so here we go. I made this one a little bit prettier. So here we have a solid sphere, radius R. And if it didn't have any friction on that ramp, that ball would just slide down. but there has to be friction in order for it to rotate. So that friction is what's actually causing the torque. So that's why you'll see problems and they'll say, oh yes, it rolls without slipping. Like it has to be specific with that. You have to have it that way. So the moment of inertia for a solid sphere is 2/5 mr squared. So what you want to do is draw the forces where they act. So we would have, we would have force of gravity down to the ball. The normal force is going to be from here, perpendicular to the ramp. Now remember, it's not like a normal free body diagram because this is actually drawing the forces where they act. Now, both of these go right through the axis, so how much torque do they produce? Like if we were to draw this a little bit bigger, and we were to say, here's my axis of rotation, and I have a normal force going up through like that, right? So if you were to draw a vector, the lever arm from the axis of rotation to the point, that would be my R, but what's the angle between my force and my lever arm? There's no angle, right? What's the sign of 0? Yeah. So anytime a force passes through your axis of rotation, it doesn't produce any torque. Yep. So what Emma was just asking, if you were saying the normal force goes right through the axis of rotation, the force of gravity acts straight down from the center of mass. Those two guys don't do any torque. They don't create any torque. However, we have friction that acts this way. So here's my frictional force. I didn't label him, set it up. So Fn and Fg produce no torque. So in other words, they don't do anything to help that ball roll. The force of friction helps it to roll. So knowing that, you got to figure out your frictional force, right? Let's start with alpha equals the sum of all our torques. And you notice that I write it both ways. It's either the sum of all the torques or net torque. It doesn't matter which way you write it. So we just kind of interchange them so you get used to seeing them. So it's going to be my force of friction times the radius, right? Because if I were to draw, if I want to find that lever arm, I'm going to go from the axis of rotation down to where, and it's already nice and 90 degrees. We love it. So it's all of it acts. So force friction, and then over my moment of inertia, which is 2/5 mr squared. Now our goal is to find this acceleration. When you see A, I'm talking about this, what you're talking about is the acceleration of this center of mass. So if this ball, you saw it rolling, but it still gets down there like that. So now what we're going to do, I'm going to go to the next slide just so you see. We want to find A. Now remember, this frictional force is the only force. This is my radius. We did our net torque equation equals the force of friction times the radius all over 2/5 mr squared, right? Your next step is to sum up all your forces in the x direction. And I'm just going to specify that that's the acceleration of the center of mass. So this ball, we're going to go, and we're just looking at the center of mass. We know that that center of mass doesn't rotate. Everything's rotating around it. So this would be our center of mass. So the acceleration center of mass. Yes? Okay, so just remember, when we're on a ramp, we tilt our axes. So we have our y-axis this way, and this is going to be our x-axis this way. Now we need to go back and get that force again. Fc. And then, why do we need that? Because we're trying to sum up our forces in the x direction. So we need also, remember, our normal force. We need that guy back. And then we need to break this up. So there's a lot of good review here, right? Because we need that normal force to get our frictional force. How do we get our frictional force? MuFn. How do we get our normal force? We need to break up our gravitational force into the components, because we need just the stuff in the x direction. So, here we go. And remember, if this angle is theta, that this angle is theta. So we've got the x1 is mg sine theta, mg cosine theta. Awesome review. All right, so we know in the x direction, we're going to get mg sine theta is pulling it down the ramp. That's the weight of the ball in the x direction, minus that force of friction is going to get the center of mass of that ball to accelerate down. You can then blow up our, you can get mg sine theta minus mu mg cosine theta equals ma. Okay, so now we have these two equations, right? We need what sometimes is called like a bridge equation. What equation is going to link our angular acceleration and our linear acceleration? You guys remember? This guy. So was that a good one or not a good one? That's just an okay. Okay. This is going to be our link to a whole lot of stuff. So remember this. keep him in the back of your mind. So you could just solve this for alpha and plug this back in. And we could say, okay, well, in that case, alpha equals A over R. Why don't we take him, put him down here, and then we can simplify. We can do some simplifications. So A over R is going to be my force of friction, which is mu and g cosine theta times R all over 2/5 mr squared. And then at that point, you can get a value for A. The simplest I got for A was, you guys can check me on this, but like this R cancels with one of those R's, this cancels with this. Oh, and the mass cancels. So I got 5/2 mu d cosine theta. So the center of mass would have that acceleration at the bottom of the ring. The key to this, when you have something that's rotating and moving, so it's different than just a pulley or something that's spinning, then we only have to worry about the angular stuff, the net torque. But if it's rotating and moving, we got to pull both of those in. So we're going to use both this equation and this equation, and we're going to link them together like so. Alrighty? You guys, any questions? Emma, you don't look happy. So you were saying that you were just kind of summing it all up in your head anyway? Let me look at it and get back to you. Yeah, let me look at you and let me look at it and get back to you. Because off the top of my head, I'm going to say probably not, because there might be more forces and you want to make sure that you are relating your linear force with your your linear acceleration and your rotational together, because it has both. So since it has both, like, yeah, if it's something easier like this, if you just did it in your head, probably, but I wouldn't want to say get into that habit, because it could get more complex. But I'll revisit it and I'll look at it and just see But yeah, off the top of my head, I am not gonna say, because I'm not positive. All right, so this guy is a, it's like a pulley, so we're going to consider it a solid cylinder that's attached to the ceiling, and then we have a string wrapped around, and then we have a mast that's going to accelerate this way. So remember, a good trick when you have pulleys is to anticipate which way it's going to rotate and call that direction positive. So in this case, it's going to be like a positive direction is down for that mast. And it just keeps everything going the same way. All right. So here is our approach. We want to find the angular acceleration of the wheel and the linear acceleration of the bucket. So you want to draw two free body diagrams and then apply the second law for both linear and rotational. So that's our goal. So start with your two free body diagrams. Delete this. So we're going to have our force of tension up, and we're going to have our gravitational down. Now in this case, both the bucket and the wheel have the same mass, so it's going to make it a little bit easier. Okay, here is my wheel. So it's free to rotate. So that support system isn't really putting forces on it because it's attached to the axle. So here's my axis. We know that that'll have a force up this way for the axle, and then a force and then we're going to have, this is my radius, and then we'll have out here, we'll have that force of tension. Okay? These guys produce no torque because they go right through that axis. This force is this distance away, so it will get that wheel to rotate. But since these guys act right here, then our lever arm is 0. There's no distance between the axis. All right. Here I'll write up the moment of inertia again. The moment of inertia for a solid disk is 1/2 mr squared, and you'll probably use that enough that you'll actually remember that because it's used for pulleys. All right, so do your net force all over the M. Uh-oh. And then do your net torque. Is it okay? And you really don't have to use the bridge equation for the very end. Let me know what you get. Remember that we said that this is going to be the positive direction down. So in that case, we're going to say that this is also positive. And the reason that we do it that way is because you have less negatives in the long run. And it just makes the math a little bit cleaner. You should get the same answer either way, but so find your acceleration of the bucket that's moving down and the acceleration of the pulley. Yes. We're just using letters. You guys can talk to Emma too. Like, she's here all by herself. So if you want to brainstorm with her, Bill, you're usually good for that. So hopefully you got to this point and this point, yes? So at this point you can use your bridge equation. You know that alpha equals A over, in this case of B capital R. And you put them in here. Let me see if I can get. I'm going to go to the next step. 6. Like the reader. So So, this cancels with this cancels with this. So we could get an expression for our force of tension in terms of A, right? So if we do that, we would end up with 1/2 A. And look, we go here. Plug him in there. and get me something good for acceleration. What do you guys got? This is just a little bit of algebra now. So the angular acceleration of the wheel is slightly less than the linear acceleration, but that linear acceleration, the big idea here is that your linear acceleration is the same as your tangential acceleration. So around this wheel right here, here's your tangential. That is going to be the same all along for that bucket. So here, 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 here. And that's why we're able to relate the acceleration of that object that's moving downward with the tangential. And that tangential is just related using that bridge equation, A equals R alpha. All right, we definitely have time for intro to the kinetic energy part of it. So we already started to talk a little bit about this when we first started talking about movement, right? So we said that regular translational kinetic energy is 1/2 mv squared, and our rotational kinetic energy looks almost identical, except for the fact that instead of mass, we use moment of inertia, and instead of linear velocity, we use angular velocity. So it looks like 1/2 I omega squared, and we measure that in joules. And it's not a new type of energy. It's just that from this point, we haven't looked at things that were rotating and moving. We've only looked at things that were moving linearly. So let's look at something like this. So we have two masses. M1 is going to be greater than M2. We want to know how fast is M1 going to be going right before it hits the ground. So we have a bunch of different information here. We're going to say that this is R. And we're going to start with conservation of mechanical energy. So conservation of energy tells us that all the energies added up before are going to equal all the energies after. The difference is this has a mass. So now this has, we've always said, a massless pulley, and we've always been able to say that the tensions were equal. Now they're not equal, because we're going to have more tension on this side than this side in order to get it to rotate. All right, so the way that this is going to go when we let it go, it's going to go down this way. So just keep that in mind too. In the beginning, before we let it go, the only energy we have is all potential energy. So it's all gravitational potential from mass 1. Afterwards, let's think of all of the kinetic energies, all of the potential energies, everything that we have going on. Once M1 goes down and M2 is now high up, what are we going to have? Let's start brainstorming. So it's right before it hits the ground. Go ahead, Emma. The first one, Will, right? So it's right before. So this guy's still going to have some kinetic. So there'll be kinetic energy from the second mass too. Awesome. Plus, yeah, so the wheel's going to have some rotational. So now we know what we're looking for. Now we can go in and we can actually say, we're going to say that, let me say, hold on a second. Yeah, so we're just going to use it like M1, M2, and then we can say MP for pulley. How's that? So we'll say M1, M2, MP for pulley. So now this is going to blow up. We're going to have a lot of terms here. So MG, M1GH before, and then you guys can help fill this in. We get 1/2 M1 V squared. Those guys are going to be moving at the same speed, just opposite directions. So we don't have to worry about those subscripts. Plus 1/2 M2 V squared plus M2GH plus 1/2 I omega squared. So this is sort of like when we started with conservation of energy, and we only looked at things with kinetic and potential, and then we added in springs. Well, now all we're doing is adding in some kinetic, some rotational kinetic energy. So it's not any new concept. You always start with your conservation. You figure out the befores and the afters, and then this time you now have some rotational kinetic energy, which is just 1/2 I omega squared. Did I write it on the other page? It's a disk, so it should be 1/2 I omega squared. So 1/2 mr squared. Hopefully. Okay, so we want to find the linear speed, and everything looks great till we get to, whoops, till we get to this guy. I didn't mean to make that. There we go. All right, until we get to him. What do you think we're going to do? Remember how our tangential speed is related. So we're just going to write our omega in terms of that tangential speed. And that's what these guys are going to do. They're all the speeds are going to be the same. Okay, so go ahead, you can plug that in. You can rewrite all of this. We're going to have M1GH equals 1/2 M1V squared plus 1/2 M2V squared plus M2GH plus 1/2. And then you can plug in your, I'm not going to have room. I'm going to do him down here. It's going to be 1/2. Then my moment of inertia is 1/2 mr squared. And then my omega squared will be v squared over r squared. And it's very nice because most of these problems, lots of stuff cancels out. So go ahead and see how you can simplify a little bit. You don't really have to go through all that algebra unless you want me to. I will. You want me to? Okay. No problem. So I have it as this. I have M1GH. Okay, that's because my R is canceled out, right? So do you get to this? All right, so what I did is I brought over my MGHs to one side, and then that way I could pull out a GH. So I have M1 minus M2 GH on one side, and then I have all my V terms on the other side. And what did I do? I'll just rewrite it. Actually, I'm going to write it like so. So all I did is I broke up that 1/4 again. And the reason is I can take a 1/2 v squared out of all of them. So here I'm going to have M1 minus M2 GH. And then I can pull out a 1/2 v squared out of all of those, and I'll be left with M1 plus M2 plus 1/2 mass of the pulley. And then at that point, it's pretty straightforward to solve for the speed. So, although it's not pretty, it will look like this. V equals okay. So if you remember solving for Atwoods and stuff, like on the bottom, when you were looking at the acceleration of it, you know, there was just those two masses at the bottom. Now this also plays in to, now the mass of the pulley also plays into it. Okay, but the idea is still the same. We are going to use conservation of energy. And then we got pretty, yeah, we went pretty far. All right, we're going to do this ramp one tomorrow. And then I also have one I'm hoping to get to. Can I just show you and then I'll let you go? I'm sorry, I know I'm over. But if you look in the materials, there's a pretty complex looking one. If it got there. I didn't upload it. Shoot. I wanted you to read over it tonight just so you're familiar with it, but I'll send it out via text because I forgot to upload it. I could probably do it now. Actually, it'll be here. You can look at it, at least read over it, so that you can just be familiar with it, because it's kind of complex. Okay, so I'm going to add a page. And then you should be able to go a little bit further in your WebAssign if you have time tonight. Try one or two of them. But look at the topics at the top. If it's dynamic, you could probably attempt those. If it's kinetic energy, you might be able to. You should be able to at least do the beginning ones. And then read this guy over. So this one is going to have all sorts of fun stuff. Okay? So just read it over and I'll see you tomorrow morning. And we will fly through it. Okay? Awesome. Thanks. I think it's this one. I'm worried about Lauren. It's just seems okay. All right, see you kids. How do you feel about that? Lots of math. It wasn't? Okay. This guy, wait, no, that's not it. This guy, I don't know why he didn't open. Anyway, this one will be fun. Yeah, so we're going to look at how much mechanical energy is transferred to thermal energy due to friction. So that's important.